Today we're going to start talking about a new topic, which is Grover's algorithm. Okay, so we're going to leave this paradigm that we've been working in with the Bernstein-Vazirani algorithm, Simon's algorithm, Schwar's algorithm, and the hidden subgroup problem. So, kind of all of these algorithms were of the form Fourier transform, query, Fourier transform. So now we're going to see something different, okay? And along with Schwar's algorithm, Grover's algorithm is, one of the two very important early quantum algorithms. And Grover's algorithm has had, tremendous influence on quantum algorithms. It shows up in all kinds of applications to different problem areas, okay? And the reason for that is that Grover's algorithm solves a very general kind of problem, which we call a search problem. Okay, so the basic setup is the following. Say that we have some Boolean function f, and we want to find an x such that f of x equals 1, or conclude that no such x exists. Okay, that f is the all zero function. And there's a very famous problem in computer science, which is of this form, okay, and that is the three-sat problem. Okay, so I have an example of that here. And to describe this example, let me let me define a few terms here. Okay, so we're going to start off with a literal. Okay, so a literal is just a variable or its negation. Okay, so this is some xi or the negation of xi. Okay, and now these expressions here are what we call clauses. Okay, so a clause is just an or of literals. Okay, and now this whole expression here, this is a formula in what's called conjunctive normal form. Okay, so this is an and of clauses. Okay, so in the three-sat problem, you're given a formula in conjunctive normal form where each clause has at most three literals. Okay, and the problem is to determine if there exists a satisfying assignment to that formula or not. Okay, so you see that this formula, it defines a function f, right? Because for every assignment to the variables, right, every 0, 1 assignment to the variables, then you can plug those values into this formula, and the formula will either evaluate to true or it will evaluate to false. Okay, so this formula, defines a function of this form, and the three-sat problem is exactly this problem. So we want to determine if there exists a satisfying assignment or not. Okay, so in this particular case, um, we have a satisfying assignment. For example, just the all zero assignment. So if x1 is 0, x2 is 0, and x3 is 0, then I've put in blue here the literals that evaluate to true, and red the literals that evaluate to false. And you see that in every single clause, we have at least one literal which evaluates to true. Okay, so the formula overall evaluates to true. Okay, and three-sat, we believe it's a hard problem to solve classically in general. And it's kind of the canonical example of a NP complete problem. Okay, so we're again going to study this generic search problem in the query setting. Okay, so we suppose that we have query access to this function f. Okay, so basically we can ask the oracle, what is f of x, and it will tell us 0 or 1. Okay, so I can ask questions of this form, and our task is to find an x such that f of x is equal to 1, or determine that no such x exists. Okay, so you can show classically that a randomized algorithm is going to need to query, at least a constant times 2 to the n, make at least a constant times 2 to the n many queries in order to solve this problem, uh, with constant probability. Okay, and in 1996, Grover came up with his algorithm, so a quantum algorithm that can solve, this generic search problem in the query setting with just the square root of 2 to the n many queries to f. Okay. So although, this is maybe only a quadratic speedup, again, Grover's algorithm finds a tremendous number of applications because this kind of generic search problem comes up in so many different places. Okay, so that's one reason why it's such an important algorithm. Okay, so for our first little introduction to Grover's algorithm, we're going to start off with a very simple case where f is just a function on 2 bits. Okay, and additionally, we're going to assume that there is exactly one x such that f of x equals 1. Okay, so in fact, there's only 4 different choices for what f can be. So f is either this function where 0, 0 maps to 1, everything else maps to 0, or 0, 1 maps to 1, everything else maps to 0, 1, 0 maps to 1, or 1, 1 maps to 1. Okay, so we're basically promised that f is one of these 4 functions, and we want to determine which one it is. Okay, and we're also going to assume that we have a phase oracle for f. Okay, so like we talked about before. So we have 2 registers here. So x holds, the input that you want to query, that you want to evaluate f on, and a second, just a 1 qubit register, which is kind of like a control register. So, when b is set to 1 and we make this query, then we're going to get a phase here of -1 to the f of x. Okay. And then when b is set to 0, then we just act as the identity, so nothing happens. Okay, so this is our phase oracle. And now let's see how we can solve this problem, when f is just one of these 4 2-bit functions. Okay, so we're going to start off in a very familiar way. We're going to create a uniform superposition on the first 2 qubits. And I'm just going to set the control qubit, this third qubit, to be 1. Okay, so I do this not here. And then we apply the oracle. Okay, so after this, the Hadamard's and the not here, then we're just in the state. Maybe I'll write it here. So that puts us in the state sum over all x, x 1. Okay, so okay, I'll just omit the normalization here, okay? And it looks like it's also omitted here. So this first block of gates prepares this state, and then we apply the oracle, and that maps us to this state. Okay, so we have a sum over all x, -1 to the f of x, ket x, ket 1. Okay, good. So now let's see what this is in the case of our different oracles. Okay, so when f is such that 0, 0 is the input which maps to 1, then we're in this state. And when f is such that 0, 1 maps to 1, we're in this state. 1, 0 maps to 1, we're in this state. And 1, 1 maps to 1, we're in this state. Okay, so right now, we don't know what f is, but we know that we're going to be in one of these 4 different states. Okay, and so now we want to determine, which of these 4 states we're in. But these states are all orthogonal. Okay, so we can actually distinguish, we can determine which state we're in with certainty with the measurement. Okay, and concretely what we can do is, apply this unitary whose columns are just, our four possible states here. Okay, so I'm just making a matrix with these vectors as its columns. Okay, so that's going to pick out which state we're in when I apply this unitary. Okay, so when I apply this unitary to my state, and then I can just measure in the computational basis. Okay, so if I get 0, 0, then I know I have the f where f of 0, 0 is 1, and etc. Okay, so basically the measurement tells me exactly which f I have. So this is just a tiny example, but it already shows you that something interesting is happening, right? Because we're able to determine, which f was our input out of these four choices with just one quantum query. Whereas, classically, if we wanted to determine which of these four choices our input was with certainty, then we'd actually have to make four queries. Okay, so already something interesting is happening. Okay, so let's also just talk about how to implement this algorithm with a circuit. Okay, so not just look at the query complexity. Okay, so you see that we performed this unitary here, right, R. So let's see how we can implement that with a circuit. Okay, so you see that R actually has, all of the entries are the same except for the main diagonal here. Okay, so so R is actually just a rank 2 matrix, and we can create R just by, taking the rank 1 matrix, so which is just the uniform superposition outer producted with itself. Okay, so that would just create the matrix here where all entries are equal to a half. Okay, and then we subtract the identity from that. Okay, so that makes the entries on the main diagonal minus a half. It leaves all the other entries equal to a half. Okay, so this is a pretty simple matrix, just a rank 2 matrix. The difference of the uniform superposition outer producted with itself, minus the identity, right? And we have this normalizing factor of 2 here. Okay, so let's see how we can, create this transformation R with a circuit. Okay, so we know how to get the uniform superposition, right? That's just acting the Hadamard on the all zero state. Okay, so you see that I can equivalently write R here in this form, okay, where I'm starting out doing a Hadamard, and then I also have this Hadamard at the end. Okay, so these, bookending this operation with the Hadamard, it exactly gives me two U, right? And now bookending the identity with the Hadamard, well, since the Hadamard is its own inverse, that just leaves me with the identity again. Okay, so now we're just left with implementing this inner term here. Okay, so let's think about how we can implement that. Okay, so to implement this, what do we want to do? Well, we want to leave the 0, 0 state alone, right? We don't do anything to the 0, 0 state, but every other state we want to multiply it by a phase of -1. Okay. All right. So let's just let's ignore these Hadamards here, right? So that's just this part of the circuit, and let's focus on this part. Okay, so again, we want to multiply every computational basis vector by -1 except for 0, 0. Okay, so if I first do a z gate on the first qubit and a z gate on the second qubit, then that's going to multiply every computational basis vector by -1, except for 0, 0, of course, and also 1, 1, right? Because 1, 1 is going to pick up a phase of -1 because of this gate, and also a phase of -1 because of this gate. So overall, no phase. Okay, so now we've basically done everything that we wanted, except we still need to apply a phase of -1 on this state. Okay, so then we just do a control Z gate. Okay, and control Z gate exactly has the action of multiplying the 1, 1 state by -1 and leaving every other state alone. Okay, so now we've done exactly what we wanted. Okay, so there's a pretty simple little circuit here for implementing this unitary R. In the next video, we're going to expand on these ideas to see a more general version of Grover's algorithm for the case when f is a function on n bits, takes n bit inputs. Okay, again, assuming that there is a unique x such that f of x equals 1, as we assumed in this case. Okay, so we're going to see how to extend the ideas that we just saw to give a quantum algorithm to solve this problem with something like square root of 2 to the n many queries. Okay, so that'll be the next video.